Okay, thank you for coming. So this is the SYCL tutorial. So I'm Lee Howes. I'm a senior staff engineer at Qualcomm, and so I work on the GPU architecture team and in the compute systems organization, and we do a lot of the representation to standards as well. So as a result of that, I'm also co-specification editor along with Maria on SYCL and also on the OpenCL specifications. So I've been quite heavily involved with the development of all of these specs. So this tutorial is a joint effort between Qualcomm, AMD, and CodePlay. And so it came in 5 parts. So it's kind of accidentally this trilogy in 5 parts, courtesy of Douglas Adams. So I'm going to start with a general introduction to SYCL, fairly high level, summarizing the goals and the features of the specification. And then we're going to talk about some of the features of C++ that make SYCL interesting and how the two relate together. We have an open source parallel STL implementation built on top of SYCL. That's a work in progress, but that partly shows the capabilities of SYCL and partly shows the direction we want to go with this. Then we have some discussion of the tricycle open source implementation of SYCL itself. And then finally, we're going to have a hands-on interactive session based on CodePlay's SYCL implementation, which is why there was an email about virtual machines and making sure that VirtualBox or something similar was installed. And so we'll be distributing USB sticks with the virtual machine on them a little later. And so that session, I think, will be after the coffee break. So that's how this should be structured. So starting with a bit of background, for a long time now, C++ support has been a common request for OpenCL. And we've had recent discussion and recent presentations about C++ support in the kernel language for OpenCL. But even with that support, there is a weak link between the host and kernel code. And people often solve this using like stub generation scripts and things to try and firm up the type, the ABI connection between the two. But making that interface strongly typed as part of the specification is really a stronger solution. And in addition, the C++ standard itself is modernizing, and we're seeing a lot of interesting features coming in, the parallel STL being one of them, a lot more strong concurrency features, and a very good set of interface classes and things that are just improving the overall standard of C++ for this kind of workload. And so that makes a very nice way to evolve an OpenCL-based solution to integrate really cleanly into C++, into standard C++ with pretty standard idioms, and to allow us to build on top of it with type-safe interfaces and so on. So we decided to define a standard for SYCL. Sorry, the PDF generation of this went a bit odd. For OpenCL that addresses some of these issues. So we call this SYCL, which is pronounced SYCL fairly obviously because that's how I've been pronouncing it. This is a royalty-free cross-platform C++ programming layer that builds on top of the portability and efficiency concepts that we have in OpenCL, and in theory with little or no loss of efficiency. Indeed, in many cases, like so often is true with C++ and templating and efficient interfaces, actually a gain in efficiency for real code. And so this is intended as a higher level model, although realistically the intent is to give full access to the lower level control when necessary. So that is only true as far as the programmer decides to take it. So SYCL is a single source C++ specification defined without any language extensions at all, and this is a fundamental design decision of SYCL. So that means that the SYCL code will build through a perfectly standard C++ compiler. It obviously wouldn't get OpenCL device support through that standard C++ compiler, but it gives a convenient fallback. And this means you have a well-integrated development cycle. So the source code contains functions that can be used on both the host and in the device code. It allows you to construct reusable generic structures that can be mapped across between devices, algorithms that are templated on different operators that you can efficiently map, and that's where the STL comes in. And in particular, you have this very strong type-safe interaction between the host and device code because you maintain this tight link. So here or yesterday specifically, we've launched the SYCL 1.2 specification. So this is now public and official. This is based on earlier provisional specifications that you may have seen talks on. We have incorporated feedback from developers, so the specification has changed, and we'd like to think improved. We've streamlined a lot of the interfaces to better match C++ idioms where that made sense. And so that should be good for C++ developers trying to get into this to really naturally convey the way they would program. And we made some consistency fixes with a view to incorporating OpenCL 2.1 features as that moves on, so that we have a stronger plan for the future as we've seen the other specifications evolve, which we've also released provisionally recently. And these specifications are available from the Khronos website. So the overview of SYCL is that we have a structure where we see user application code, and then various different types of libraries. So like OpenCL itself, SYCL is really intended not only as a high-level programming model for people to use, but as an infrastructure component for people to build efficient portable libraries on top of. And that's why matching some of the standard C++ idioms is so important. So we might see OpenCL giving us a portability layer to different devices, and then SYCL targeting that. But on top of that, we will hopefully see, and we're starting that with the parallel STL, a set of different template library interfaces so people can build complex applications, maybe without even seeing the SYCL or OpenCL code itself, but allowing plugging in of components and lots of innovation at the high level. And of course, these same libraries might have consistent interfaces to target other technologies, like directly go through to standard C++ threading libraries and things. And again, the STL is a good example of this. So this is a SYCL program, a very simple one. What we're trying to show here is that this is this single or shared source model where we see host and device code in the same flow. And of course, this at first simplifies basic examples. This is an entire program. In terms of lines of code, it's actually barely any shorter than OpenCL code with the C++ headers can be now. But an important point is that it's all in one file and has a type-safe interface. So we have host code in there, the top and bottom. So when we create our data structures, so we can create all the data structures we need. We can create queues. We can manipulate them and everything else. And of course, we can manipulate data coming out. And all of that is host code. And then we have device code that's actually going to do a parallel operation that sets this output array. And so this is obviously a trivial example of this. But we have the ability to type check the interface between this host-created buffer and the data we're assigning to it. And obviously, you know, as I couldn't show a complicated example of where that's useful, but when you build up template interfaces and things, you have much more interesting results coming from that. But this is a very simple case. So this gives us, because this is standard C++, it allows us to do an interesting build process. So at the top here, we see that we have, we have that source file that I just showed, and we run this through a standard CPU compiler, Visual Studio, GCC, whatever else, and this generates a standard object file. And this is perfectly standard host code. There's no magic in there. We also can run this through one or more device compilers. Now, the device compilers go over the code, identify the device kernels, generate appropriate underlying code for, say, the SPEAR intermediate language that runs through OpenCL, generate the binary objects for that, and then there's an implementation-defined linking step. So this is obviously a language specification, not an implementation specification. So the actual process here is left up to the implementer, and we'll see the way CodePlay's tools work for this during the hands-on demo later. But the specification is designed to allow this. Go on, Ben, you have a question.
That top one there, that CPU compiler, so your Khronos is going to provide a library that all SYCL programs will always work on the platform. You said I was just compiling an arbitrary.
You're asking if Khronos will provide a library that will just work on all platforms.
On the CPU, on all CPU
Well,
platforms.
not Khronos. Right? This is a specification. So let's say CodePlay's implementation that we'll see later, they will be providing headers with their implementation and host code, just like any host library like the STL does when you buy Visual, or you get Visual Studio, you get the STL headers. It would be similar. It's standard host code. It runs just standard. The interfaces, of course, are compatible between different compilers. Now, if you compile their headers through well, those headers obviously have to run through that standard host compiler, so that is standard code. The device code may have access to headers that are subtly different. They have some magic in them, to hint to the compiler what to do. Yeah. So that's one of the features of this, that because this is standard C++, you really can do the whole thing and just use that host path. And without a device compiler. And that's actually what the tricycle implementation we see does. This is an implementation of the library side of things without a device compiler. So we're kind of demoing both approaches today. And that could indeed act as a parallel library, but it would then be CPU only, obviously, because you've got nothing to generate the device ISA. But this allows you to have an efficient fallback path, when you don't have an OpenCL device, when you don't detect one on the system, or indeed just so that when you have CPU code and device code running, you have the standard device compiler generating efficient code on the host. So we have, as I said, this is a high-level model conceptually, but we do define the full flexibility of host code you'd want. So when we see that host code, we have default objects to simplify construction, so that in this case we just construct a default queue that takes a default device, default context, default platform, if you're aware of the OpenCL terminology that often blows up OpenCL code, and buffers that are type safe and so on. But you can be more specific when necessary. You can construct a device and construct this queue off a device and choose a specific device when you want to. And to achieve that, the library defines various selector objects for filtering the set of devices in the system. You can build your own selector types so that you can select on whatever particular feature of a device you want and plug that into the interfaces. So it's designed to give you the flexibility you'd expect. And of course, you can construct image objects and program objects, kernel objects, pull in OpenCL kernels directly, and so on. Then the device code, we abstract through this block with a handler object. So this is designed to match styles that are moving into the C++ standard with some of the concurrency functionality now. And what this structure gives you is so the kind of the ordering of operations here is traced through standard C++ types and operations. We have well-defined scopes in the language that bound the beginning and end of use of an object, and so that allows us to make use of standard C++ RAII behavior to define lifetimes of things. So there's no magic here and no need for language extensions to define lifetimes of buffers and access. The way dependencies are dealt with is that in this block, and for the lifetime of this block, we acquire access to a buffer object. So here we are saying that for the duration of this task, we're getting write access to result buffer. And obviously that write access ends here, and that means that the runtime system can do asynchronous task dependencies based on read and write access to particular buffers at particular times. And that access falls out of scope at the end. So by the time the host code here runs, this is what I mean by it being a standard host compiler, by the time the host code finishes running that block, it has constructed this task and all its dependencies and put it on the underlying OpenCL queue and constructed all the event dependencies effectively, transparently to the user. You can't write a CGH to memory. You can't, because the you could make a copy of the object, but the lifetime of the underlying entity obviously ends at the point when the submit call finishes. Yes. This is one of those things that if you follow the rules of the language, you're okay. If you start writing anything you like out to memory, then you can obviously break those rules. Yes. So this then gives you OpenCL style SPMD execution here. So in this case, this is a 1D range, and you can pass some runnable object to it, a function object, lambda, as long as it has the appropriate interface to take the ID representing the point with the appropriate number of dimensions and so on. And of course, these will match. So the range you launch over has to match the right type with the way the body of the kernel is going to execute. And so the one thing in this code that was not obvious is not standard host code or host compiler code is this naming. And this is the one place where the implementation decisions, or at least the allowed implementations of a SYCL, kind of show up in the host code. So because we are separating the host and device compilers, or at least allow a separation of the host and device compilers, and because C++ does not define how lambdas are named in the type system, we have to allow the user to provide a name for the thing they're generating so that the tools can link the host and device code together. And we concluded that this was a low cost compared to having language extensions and having to define a single source compiler approach. And if you use function objects, it's not an issue anyway, because those already have a well-defined type name. So in the kernel code, we have vector classes to represent the short vectors that people expect. We have a subset of IOStream functionality rather than printf, to have a more C++-like mechanism for outputting debug information. A lot of people do rely on printf in OpenCL code for debug, and this gives the same functionality as that. Support for the full OpenCL mathematical library that you'd expect. C++ style atomic operations. This is one case where you'll see a continuity going from SYCL 1.2 that we're releasing here to the next version of SYCL, where we already see much better defined memory model with full suite of atomics in OpenCL 2. Similarly, these same atomic styles will just expand to support that in the SYCL code. for 1.2, we have the subset of atomic orderings that we can support in the underlying OpenCL model, and those are technically the only ones that would be allowed in device code, and that a device compiler and the device library is expected to support, because those are the atomics that we can efficiently support on the wide set of OpenCL 1.2 devices where we may not have strong cache ordering behavior, for example. Now, to expose more information to the compilers and to allow the device code to be generated the most efficient way for different types of launch, one benefit you get from the single source model is you can very tightly link the way you're going to dispatch a kernel to the way that kernel is going to run. So if you think about OpenCL code, there's only one type of kernel, really. It runs over an ND range. The kernel code doesn't know how many dimensions it has, what size those dimensions are, or anything else. And the host code, you just have errors that can be reported if you launch it in a way that doesn't match. And then you have things like CL and Q task that appear different in the host code, but actually when you look at the kernel code, they're the same. And so there's a disconnect in the information there. So here we are much more explicit than that. So single task here is a scalar thing. It really, there is just one of it. It's guaranteed to just be one of it. It might execute as a single OpenCL work item with generating a single kernel body that's always going to be a 1 by 1 by 1. But you can generate that code parameterized, saying the required workgroup size is 1, 1, 1 here, and the compiler can do things with that, knowing what it's getting. We have these simple map operations, which is what I showed before. So this just has a range. It just has an ID. There's no concept of workgroups. There's no concept of local memory. There's no... so that means that when this is mapped down, it can be very flexible about the mappings. It can know what it can pad and mask out, and it knows there's not going to be any synchronization in there that's going to do any harm, and so it can generate more efficient code. Then we have more sophisticated dispatches, where maybe we have more information about the range that's being dispatched. So if we have an item, that gives us more information rather than just the ID, just the point in the iteration space. We also know its bounds and so on. We can add work groups to the dispatch, and at that point you can use local memory, you can use barriers, you can synchronize, communicate. But it's very explicit that this is different from this, and both the host and device code know that. And so that means you don't have to generate as many weird corner case checks and things. And you certainly don't have to write them. And then we have hierarchical parallelism. So the aim here is to better match the developer's intent in a lot of cases. So what the developer really wanted to do when they wrote the code was not to write lots of tiny threads and communicate between them. What they really wanted to do was think about a convolution operation. They wanted to copy the data into local memory with some bounds, and then do a convolution on it with some other bounds. And in between, they synchronize. Well, we can just allow them to write that. They write that loop that does that copy, and these bounds might be slightly different from the bounds of the convolution. And then there's an implied synchronization here, and then this loop does the convolution. So the actual way the sequence of operations you want to achieve is written in a much more natural way for the programmer, and it comes with another couple of benefits. So when you do barrier synchronization code and you try and port it to a device that doesn't naturally run multiple threads and have barriers, let's say a CPU, then you have to do some tricks here. You might implement this as lightweight CPU threads and have some switching code hidden in there. You might do loop fission, so you split the body of this over 2 loops. Well, this is already naturally structured that way. So here we have loop fission trivially. It's written in the code. And so that makes this code more performance portable to a wider set of devices. There will be cases, obviously, where the OpenCL style of synchronization is the appropriate way that you want to structure your code, and so that's why we provide both. I sense a question coming from Ben. Okay. So that was a summary of the features we put into SYCL, without going into any deep detail on any of them, because we're going to work through some of the examples. So we're going to continue now with Renan, who's up here, who's going to talk about the C++ features and how they relate to SYCL. But if you do have a question, Ben, I can take that now.
One, why wouldn't you use a typeset printf? I mean, we have already got templates. IO streams would seem like overkill.
Oh, so Ben's asking why not use a type-safe printf rather than IO streams. Because the feedback got from developers was that C++ developers didn't really want printf. They preferred that style. That was the feedback we got. Now, now IO streams can have lots of problems, but if you're restricting them to the subset that you're going to allow anyway, then we can do it okay. And your other question?
Well, your fission example,
yeah.
It doesn't really account. One of the difficult problems when you're doing big fission with respect to variables is how you handle private memory, right? To reuse it. That wasn't clear enough.
Right, so
Easier with your example than it would be with the standard OpenCL.
well, so the problem is when you have standard OpenCL code, the compiler might have to make a kind of a fission optimization where it has to try and work out which variables it can reuse in that, or has to clone, right? Now in this example, there are two things. One, variables that you just allocate in here are shared by definition, but the compiler clearly can do the standard kinds of transformation it would do to vectorize the loop to kind of privatize these per iteration. So that's the first thing. The second thing is that then when you want some more control, you want to tell it exactly what you want to do. Then we allow allocation of things that are explicitly private. And there are rules defined in the spec for what this means in terms of being used in these loops. So here we do have an example of a private variable that's written here and read here. Now clearly, if we have an example like the convolution where these loops are different dimensions, then that's difficult. But then in that convolution example, you don't care. You're not actually going to carry private memory in that way. All your data is shared. You copy into it, and then you compute on it. So it depends on what you want to do. But the interfaces give you the control to tune that.